Hey there, everybody. In this section, we are going to start Chapter 3, but Chapter 3 has a probability section at the beginning. So the probability is an annex in your book, and it's at the very back. So if you have a hard copy of the book, the probability stuff is not part of Chapter 3. We can kind of put it wherever we want it. So we are introducing probability before Chapter 3. It helps some other things become more clear later on. So this is called probability rules. And what we're going to do is a full treatment of probability. This is going to be one of the longer videos. So if you need to take a break halfway through, I understand. So obviously we're going to be doing a lot of calculator work, and there's a lot going on in this video. Probability is very important in this class, so you might have to watch this video a couple of times. On the bright side, if probability is not your favorite subject, maybe you've studied it before, you can get through this class without a great understanding of probability, but I would recommend that everybody tries to learn this at a very high level. So it's a full treatment of introductory probability, and it's all in one section. So let's get started. There's your section learning goals. I'll let you read that. All right, I am too big on this image. There we go. So let's just go through everything. So the first thing we're going to do is introduce randomness. We talked about random sampling earlier in the class, and our view of random sampling is that if you put everybody's name in a hat and draw one out at random, what does that mean? Well, that's a simple random sample, right? Is what that was, putting the names in a hat. But there's more to randomness than just that. So randomness just means that each outcome is uncertain. When you put all the names in a hat and pick one out, that's actually a special kind of randomness that we're going to see in a second. So in statistics, even if a particular outcome is unknown, we can still make a prediction based on long-term trends. And that's the whole purpose of statistics, right? So a good example that I'm going to keep going back to, and that's on everybody's mind, is the vaccine trials going on for a coronavirus right now. And if this video is still on the internet 20 years from now and somebody stumbles upon it, that is occupying everyone's mind here in 2020. How do we test whether a vaccine works? Well, they have to take large enough samples and make predictions based on those samples, and that's hard to do. And that's actually what we're going to see, stuff like that, here in Chapter 3 and 4. So the two examples I put at the bottom is if we flip a coin 3 times, the distribution of heads and tails is highly uncertain. So you could flip a coin 3 times, and you could get 3 heads. Does that mean if you flip it 300 times, you're going to get 300 heads? Of course not, right? So the idea is that small samples have a lot of variation, and larger samples should have less variation if there is some long-term trend. Certain things truly are random, right? But the idea is that we can distill patterns out of the randomness and make predictions. And that's the whole purpose of statistics, right? Whether it works or not is what we're learning about, or how it works. But we need to understand the mechanisms, right? So let's keep going. So any combination of outcomes is called an event. So an event is something you name, right? And given some random process, the probability of an event is the long-run frequency or proportion of times the event would occur if the process were repeated many, many times. So let's talk about that. So this is the definition of probability, right? We're defining probability for this class as if we did this process a whole bunch of times, what is the relative frequency of occurrences as a proportion or a percent? And more about that in these notes, and also more in Chapter 3, as you will see. So probabilities of events are numbers between 0 and 1. Well, that should make sense, right? Because we're defining probability as a relative frequency, and in Chapter 2 we defined relative frequencies as sample proportions or population proportions. Sample proportions and population proportions have to be numbers between 0 and 1, so the probability because it's a proportion, also has to be between 0 and 1. A probability closer to 1 indicates the event is more likely to happen. So if an event can't happen, we just say it's probability 0. And if it always happens, or it's guaranteed to happen, it has probability 1. So it's sort of a scale, right? With 50% right in the middle. So there's 3 main types of probabilities: theoretical, relative frequency, and subjective. So I'm going to go ahead and define all of these. We're really only going to use relative frequency in this class, but it's nice to know what a theoretical probability is and what a subjective probability is. So theoretical probabilities are based on the shape or design of an object or system. So games of chance are theoretical probabilities, right? A coin has 2 similarly shaped sides, so both sides have roughly equal probabilities of showing when flipped. A coin itself doesn't favor one side over the other, right? And that's based on how it's designed, right? It's designed to be as even as possible on both sides. Standard dice have 6 similar sides, so all 6 sides have roughly equal probabilities of showing when rolled. And when a calculator or a computer picks a random number, it simulates a process like a coin flip or a dice roll. So this is really important because we're going to be doing a lot of simulations in Chapter 3. And you have to understand that when we do these simulations, the computer or the website that we're going to use is essentially simulating a dice roll or simulating picking names from a hat or something like that. So if the outcomes are equally likely, hold on one check. Oh, there you go. If the outcomes are equally likely, like a coin flip or a dice roll, then we define the probability as P parentheses event. Okay, so what that means is you put the event in parentheses, like that's the name. So events are named outcomes, like groups of named outcomes. So it's the number of outcomes in the event divided by the total number of outcomes. So putting the names of all students in your class in a hat, then drawing one out to select a student, is a random process that theoretically has equally likely outcomes. So if there's 20 students in your class and your name is in the hat, you have a 1 in 20 chance. One outcome is your name. There are 20 total outcomes, so it's a 1 in 20. And that's what we normally use in statistics, something like this. So if we flip a coin 3 times, there are 8 equally likely outcomes, right? And you can see all the outcomes, and this is how we normally list outcomes. We normally put them in curly brackets or curly braces and just list all the outcomes. So you could do 3 heads, 2 heads and a tail, a head, a tail, and a head. So the outcomes are distinct, right? So because we're flipping a coin 3 times, these 2 outcomes are not the same, right? So just keep that in mind, right? So the order matters if you're doing multiple things. Well, these are all events down here, right? So exactly 3 heads. What's the probability of exactly 3 heads? Well, only one event is 3 heads, and there's 8 events, so the probability has to be 1 in 8. On an exam or on the homework, it's really preferred that you use decimals, not fractions, but just follow the instructions on the individual problems. So obviously, just if you're not sure, just use a calculator to do everything, right? So there's the calculator. Oh, wait. Let me use this guy. I forgot I had it on here. If you're not sure, just type it in. Don't guess. Don't do stuff in your head. You have these really fancy, expensive calculators or apps. Use them. What about exactly 2 heads? What's the probability? Well, here's 2 heads. Here's 2 heads. Here's 2 heads. So there's 3 outcomes that have 2 heads. So the probability is 3 out of 8. Right? Again, pretty easy stuff. And so on and so forth. What about at least 1 head and 1 tail? This one doesn't have any tails, so not that one. This one has at least a head and a tail, a head and a tail, head and a tail, head and a tail, head and a tail, tail, no head. So there's 6 of them that have at least 1 head and 1 tail. So that's going to be 6 out of 8. And again, you can see that we can ask these questions in wacky ways, like the first flip is a tail. What's the probability that the first flip is a tail? Well, you can see tail, 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 tail. There's 4 of them, so it's 4 out of 8. So this is just an introduction. We're counting the number of outcomes, dividing by the total. One thing you're going to realize, and this is different than what we did in Chapter 2, is the denominator will always be the total. Always. Okay? So let's keep going. But it turns out not all outcomes are equally likely, as you probably guessed. So we want to at least briefly address what happens if the outcomes are not equally likely. How do we deal with that situation? Well, it turns out that even if the outcomes are not equally likely, we can still use the formula. So watch how this works. If we toss a water bottle onto a flat surface, it might land with the cap up or on its side. So you guys have all seen this before, right? Do we think the outcomes are equally likely? Right? Well, no, right? We don't think that the outcomes are equally likely. But we can still figure out the probability of landing cap up, but we're not going to do it using the theoretical probabilities, right? We're not measuring the shape and computing it. So theoretical probabilities work great with coins and dice and names in a hat and calculators doing random numbers. It works great for that. Doesn't work so great for objects in the real world because they're not equally likely. So what we use instead is what we call relative frequency probability. So that's what we use, right? It's basically your p hat. So it's computed directly using data from an experiment or an observational study. So if Carson tosses a bottle 50 times and it lands cap up 13 times, then her proportion of successes, probability of cap up, is 13 out of 50. And it's 0.26 or 26%. And so the idea here is that this relative frequency, this is the estimated chance of success or estimated probability of success. So anytime Carson flips a bottle, we estimate it has a 26% chance of landing cap up. So here, the equally likely outcomes is we're saying every flip of the bottle has the same chance of landing cap up as every other flip. We're not saying that cap up and on its side are equally likely. So you can see how we can use data to still compute the probability. So this is just a p hat. This is just a sample proportion. And this is what we learn in Chapter 3, and it's the method most often used in statistics. So it's really the only method we use. I'm only introducing theoretical probabilities and subjective probabilities, just if you hear about those things in the world, that you know what they are. So the last type of probability is subjective. In other situations, we may talk about the probability of an event, even though repeated trials are not feasible. You might wonder, what's the probability that I get an A in this course? If you have 101% in the class right now, probably pretty good. If you have a 65% in the class, probably not so good. But you can't do repeated trials. It's just an estimate based on your belief about something. Or what's the probability it rains tomorrow? Don't know. I'm going to say a 0% chance, but it still could rain. Nobody knows if it's going to rain or not, and you can't do repeated trials and go back and start the day over and over again. Just can't do it. So subjective probabilities have value, but we don't use them in statistics to compute anything. Those are best used for opinion polls and that sort of thing. All right, now we're going to look how to combine events. So outcomes and events can be combined in various ways to form new events. We saw it earlier with the coin flipping. Let's go into more detail. We might be interested in the probability that 2 events occur simultaneously. At least one of the 2 events occurs, an event does not occur, or one of the events occurs if the other one occurs. All of these have special names, and we're going to go into detail with all of them right now. So the first thing we're going to look at is this example about the Rock and Roll Hall of Fame. So this data is current up to 2015. I have not yet updated it, sorry, but this is the same data the homework uses, so I haven't messed with it. So up to 2015, the Rock and Roll Hall of Fame has inducted 303 groups or individuals. So what we're going to do is we're going to name events. We're going to call one event F, and that's the event of the band has female members, or if it's an individual, that the individual is female. And we're going to call MP the event of being a music performer. And the table at the bottom shows the data. So this is a frequency table. It's a two-way table. So we can compute relative frequencies, right? That's what we want to do. So you can see 38 out of the 303 members are female music performers. 9 are female not performers. So that's things like songwriters, managers, things like that. And then no female members, 168 music performer. No female members, not a performer. So there's really only 4 sort of combinations of categories, right? There's 4 categories, so there's 4 ways to combine those categories together. All right, so now let's compute some probabilities. So find the following probabilities. Find the probability. So look at what we're given. We're just given PF. What does that mean? Well, this means the probability of F. What's F? Got to go back and check. The event of having female members or being a female. So what's the probability that if you select a member of the Rock and Roll Hall of Fame at random, that you get one that is female or has female members? Okay, so we're taking everything out of the total, right? So just build your little fraction here. So everything's always out of 303. So probability of female, how many females are there? 47. So it's 47 divided by 303. Right? And you can check the answers. They're all on the next slide, right? Again, I'm rounding to 3 decimal places. So you're going to want to double check that you get all the same answers I do as we go through this. What about the probability of a music performer? Well, how many music performers are there? 206, right? So 206 divided by 303. Again, you can type it in however you want. Doesn't matter. Right? So you get 0.680. Does that look like the answer over here? Sure does. And so on and so forth. So I'm going to leave the answers on the calculator so you can see them, and I'll keep flashing back to the solutions here. Next one, probability of being female and a music performer. So and here does not mean add, okay? And means both. So how many people in the Rock and Roll Hall of Fame are females and at the same time music performers? Well, here's all the females. Here's all the music performers. So it's just this 38, right? So it's going to be 38 divided by 303. Let's look here. Probability of music performer and female. So here's all the music performers. Here's all the females. It's 38 again. We already computed it. So I want you to think about this. Female and music performer. Is that always the same as music performer and female? Or is that just a coincidence in this problem? I'll address it in a second, but I want you to think about it. If you need more time to think, pause the video and come back. And for part E, probability of not a music performer. Well, 97 are not music performers. So that's just going to be 97 divided by 303. Right? So you can check all the answers. So we already checked the other ones, but you can check everything else. And then that leads us to, wrong button. That leads us to this question, right? The answers for C and D are the same. Is it always true that the probability of A and B equals the probability of B and A? So think about it. Did you think about it? What'd you come up with? That's correct. It's yes. Because we're matching categories, the order you match categories doesn't matter. Whether you're a female and a music performer or a music performer and a female, each individual person is still the same person, so the count is still the same. So what that means is that if you see an and, you're allowed to switch it. Just remember that. So here's some common combinations of events. We've already addressed and we've addressed not. We haven't seen or, and we haven't seen if. We will see all these. So, and means the event satisfies both conditions simultaneously. That's called the intersection or the joint probability. Either one's fine, and you'll see both of these used. Or means the event satisfies one or the other or both. In math, the word or is inclusive. So it would be like at the Olive Garden, soup or salad or both. But at the Olive Garden, soup or salad means you don't get both. But in math, you do get both. And that's called the union. Not, we already saw what not looks like, and it just means the event doesn't happen, something else happens. That's called the complement. And lastly, B if A. That means event B happens if A happens. That's called a conditional probability. You're going to want to remember this stuff. It comes up absolutely all the time in this class. So let's jump in and see the probability types that we haven't addressed yet. So the first one is the complement. So for any event A, the event either happens or it doesn't happen. It might seem obvious, but we need to say it. So the probabilities of both options must sum to 1. The probability that something happens plus the probability it doesn't happen has to be 1. Remember, 1 is the largest probability possible. Well, that leads us directly to the complement rule. So all we have to do is take this equation and subtract the probability of A from both sides, and we get this. So if we want to find the probability that something doesn't happen, and we know the probability it does happen, you just take 1 minus the probability it does happen, and it gives you the probability of not A. So we actually did that already, right? Whether you know it or not, in the previous problem, right? So here's an example, right? So if we take the probability of being a music performer was 206 out of 303. So we just take 1 minus the probability of being a music performer, 26, right? So we just did that one in the previous problem. And if we hit enter here, you get this 0.320, which is the same as the probability we computed before. So it doesn't matter what order you do it in. But the way this works is sometimes you're given less information than the table of values that we saw, right? So in this problem, with the Rock and Roll Hall of Fame, we were given this big table of values. Sometimes you're only given a single number and you need to use the formula. So if we were just told just this one number and needed to find the complement, we would just do 1 minus the probability of music performer, and we would get 0.320, which is the probability of not being a music performer. Again, so we just see that we computed it 2 different ways. All right, and so this is a powerful rule, and we will keep using it a bunch, as you will see. Next up, the additive rule. So the additive rule is how we compute OR probabilities. So when you see OR, you have to use this formula, again, unless you're given a full table of values, but that's rare. Sometimes you're just given little bits of information, and you have to plug everything into the formula. Okay, so the additive rule says probability of A or B is the probability of A plus the probability of B minus the probability of A and B. So that might seem like a weird formula, like where does this come from? But I'm going to explain it, then I'm going to show you the example, and I think you'll see where it comes from. We need to subtract probability of A and B because it has been counted twice. It's been counted as part of probability of A and once as part of probability of B. I know that's a little abstract. Let's do the example, and you'll see where this comes from. So find the probability of female or music performer, right? So what we're going to do is use the formula. Okay, so we're going to use the additive rule, we see an OR, and then we're going to use the formula. Now, we've already computed these numbers in a previous problem, but let's go ahead. I'm going to compute it again from scratch, right? So probability of female was 47 out of 303. right? Then we add the probability of a music performer, which was 206 out of 303. Then we subtract the probability of female and music performer, right? So that was 38 out of 303. So here you can see I put the fractions in. Here in the example, I used the decimals because we had already computed these numbers in a previous example. But I wanted to show it again live just so you can see what it looks like. And here you can see where this stuff comes from. So look, if we're adding all the females, that's 38 plus 9 to get us this 47. If we're adding all the music performers, that's 38 plus 168 to get us this 206. But we just counted this 38 twice. We counted it in this column and we counted it in this row. Well, you can't count something twice, that doesn't make sense. So you have to subtract it off, right? And that's why we subtracted the 38. And that's why we got our answer. So you will have a sheet with formulas on it for the exam. So don't worry about not knowing the formulas. You're going to need to know the formulas to do the homework. Keep everything in front of you when you're doing the homework. Don't guess. Go back, look at the examples, and just do it the way I'm doing it. I can't go over every problem. This is already probably the longest video we're going to do all semester. I don't have time to go over every kind of example. I'm just going over little bits of everything, and you're going to have to kind of work out some of the more difficult problems on your own. Give it an honest effort, and if you need help, ask for help. All right, next up. Disjoint events. This is another vocab term. So if events A and B have no common outcomes, they are called disjoint. So that kind of means what you think it means, right? Disjoint means it can't happen at the same time. In other words, when events A and B are disjoint, the probability of both occurring together is 0. It's impossible, right? In this case, we use the formula, probability of A or B equals probability of A plus probability of B for disjoint events. So what we're really doing here is taking that big formula for the additive rule, and probability of A and B is 0, so we don't even have to write 0. You don't have to write minus 0, so we just leave it off. So this is actually not used that much in statistics, but it does come up from time to time, so I did put it in the notes. If you still want to use the big full version of the formula and just make this a 0, that's totally fine. You don't have to remember this as a separate rule. Okay, next up, conditional probability. Sometimes we're interested in the probability that event B happens if we already know that event A has happened. This is called conditional probability, and we write it probability of B if A. So there's the formula. And this is explained in detail in the book. If you're fine just reading the formulas and plugging the numbers in, you'll be fine with this. If you need a little bit more of an explanation, again, it's already a pretty long video. It's in the book in more detail why this is the way it is. But I don't go over the theoretical aspects of this in my notes. All right, so it's easy to remember the formula because the top one is just A and B, and we know we can switch the order on top, right? Because we saw that earlier. And whatever is after the if goes in the denominator. So the first one, the order doesn't matter, the numerator. The denominator has to be the one to the right of the if. All right, so let's compute some conditional probabilities. So what's the probability that a randomly selected member of the Rock and Roll Hall of Fame is a music performer if we already know that she is female, or that the band contains female members? So we're just going to use the formula, right? So probability of music performer if female is the probability of female and music performer. Remember, the numerator doesn't matter. You can switch that. But whatever's to the right of if goes in the denominator. We've already computed both of these, right? But let me show you something on the calculator. So as we saw in an earlier problem, I went ahead and computed everything live on the calculator versus what's in the notes. Let's make sure that that works, okay? So what we're going to do here is we're going to do a fraction. Ooh. And in the numerator, we need another fraction. So I'm actually going to put it in parentheses. So probability of female and music performer. We know that's 38 out of 303. If you don't want to type it like this, if you want to type it like, some of you might prefer this. I should have shown you this. Hold on. Let me show you this. Some of you might prefer this. You can build a stacked fraction on top of a stacked fraction like that. You might prefer that. So this is 38. What did I just do? Oh, geez. Keep clicking the wrong button. 38. There we go. 303. And then in the denominator, do the same thing. Just build another fraction down there. You might prefer this. You can see why I didn't put this in the notes, because it would take up so much space. Probability of female, we already know, is 47 out of 303. 47 out of 303. Right, and you can see that the stacked fraction. So you can also see that the rules of dividing by fractions tell us this should be 38 out of 40 over 47. Right, because it's flip and multiply. When you multiply, the 303's cancel, you'll get 38 out of 47. Right? But look at what happened here. The calculator tells us it's 0.809. Why does this say 0.806? Take a second and think about it. So here's why. On the homework, if the homework wants 3 decimal places for a final answer, I'm not sure, every problem's different, just follow the directions on the homework. You're going to need to keep more decimals here if you're rounding intermediate values. So if you don't want to round, you have to build it live from scratch every time, which is fine. I mean, it's up to you. Or you can see what I did here, that it's just 38 out of 47, that it's a conditional probability, right? So if we know that it's a female, what proportion of females are music performers? It's just 38 out of 47, right? So you're allowed to do it that way, right? All right, what about the other way? Female if music performer. Well, let's try the shortcut and see if it works. All right, so we know it's a music performer. What proportion of music performers are female? 38 out of 206. Again, you can do it the long way like I did here. That's totally fine. Now this one works out the same with the rounding. So this one, in the notes, I did the rounded version. I just wanted to show you live that the calculator gives you a different answer. So if the homework is asking for 3 decimal places, when you do the calculations, you want to keep 4. If the homework asks you to keep 2, when you do the calculations, keep 3. Or you can always do it live with fractions every time. All right, next up, the multiplicative rule. In some situations, it is more natural or convenient to start with information on conditional probabilities and use it to find the joint probability of 2 events. To do this, we rearrange the conditional probability rule to get the multiplicative rule. So if you're not given a table of values, maybe you're told the probability that something happens, and then you're told the probability that something happens if something else happens. That's called the multiplicative rule, and we're going to see it in the next example. So suppose you have 3 white socks and 4 black socks in a drawer. You pull 2 socks out at random. Find the probability that both socks are black. So right away you can see that this is a very different type of problem than what we saw with the Rock and Roll Hall of Fame. With that Rock and Roll Hall of Fame questions, everything was given to us. Here we're not given all of the information. We have to compute things. So the first thing we want to do is name your events. So the probability both socks are black. Well, we have to use this formula somehow, right? So if we're trying to say that this is both socks are black, then A will be the first sock is black, and B will be the second sock is black. So if we get first one black and second one black, that means they're both black. So we define events A and B because we have to use the formula, right? And so that's kind of the challenge on a lot of these, is figuring out how to use the formula. So notice we start with 4 black socks out of 7 total, that we're given that in the problem. So the probability the first sock is black is going to be 4 out of 7, right? So the probability here, this is going to be 4 out of 7. But what's going to go on here? If this is 4 out of 7, look at what's going on here. What's the probability the second sock is black if the first one is black? Well, if the first one is black and you pull it out of the drawer, then there's only 3 black socks left in the drawer. But there's only 6 socks total left in the drawer. So you're going to have 4 sevens, 4 black socks, 7 total, times 3 black socks, 6 total. Both of these have to be true, so you multiply. 4 times 3 is 12, 7 times 6 is 42, and round it to 3 decimal places. So that's how you use this multiplicative rule. You always multiply events when you have to have one event, then the next one, then the next one, then the next one, right? But you need to be given enough information to use the conditional probability. All right, let's keep going. Independent events. So events A and B are called independent if the probability of B happening is the same as the probability of B if A, and the probability of A is the same as the probability of A if B. So a lot of folks have trouble with this definition. So sort of an easier way to think of it is in green at the bottom. The outcomes of one event don't affect the probabilities of the other. Independent means they have no effect on each other. So think about that, okay? And when we do the multiplicative rule with independent events, we're allowed to substitute P of B if A with P of B, and so the formula changes to this nice formula. This is what we're going to use more in this class, something like this, where we're allowed in some situations to assume events are independent, like random sampling, right? To simplify some of the calculations. And after seeing that socks example, you can see that we don't want to compute things that way very much, because that gets pretty in-depth pretty fast. And this rule works both ways. If we want to determine if 2 events are independent, we can check their probabilities satisfy this formula. And this actually happens a lot. You'll be given probability of both, probability of A, probability of B, and you just have to plug all the numbers into the formula. If the probabilities are equal or very, very close, because again, rounding could be slightly off. If the probabilities are very, very close, then we say that the events are independent. And if the probabilities are not the same, then the events are not independent. And that's so this formula is really a test for independence. So it's definitely useful, as you will see. So suppose a basketball player has a probability of 2/3 of making a free throw, and that the attempts are independent events. If he attempts 3 free throws, find the following probabilities. So before we go any farther, I just want to back up a little bit. Here we talked about 2 events. This multiplicative rule can be expanded to any number of events, right? So if it's A and B and you multiply, then A and B and C, you would multiply 3 events or 4 or whatever. So I just want to point that out, that it doesn't matter how many events there are, everything stays the same. The formula just expands out and stays the same. All right, so if he attempts 3 free throws, find the probabilities. What are the probabilities he makes all 3 free throws? So what we have to do is similar to what we did with the socks example, right? Except we don't need to use any conditional probabilities because all these events are independent. So we name the events. Event A makes the first free throw. Event B makes the second one. Event C makes the third one. So the probability that the player makes all 3 is the probability where we can just multiply the individual probabilities. Each one is 2/3, which is 8/27, which is 0.296. So however you want to do this on your calculator is fine. I've seen people do stuff like, let's put it in parentheses, like 2/3. I've seen students do it this way, like 2/3 cubed. That's fine. However you want to do it. You don't really have to show a lot of arithmetic for these. So if the player, is a 2/3 probability free throw shooter, there's about a 30% chance he's going to make all 3, which is pretty good odds, right? All right, let's go back. What about the part B here? He makes the first 2 but misses the third. So same sort of thing as what we did before, right? So you still write out the probabilities, makes first and second, misses the third. But this one's not quite as simple. We can't just multiply the probabilities out. So makes the first one is still probability of A, makes the second one is still probability of B. But if he misses this, we have to write this as not C. Remember, you either make a free throw or you don't. So we're going to call that not, right? Missing the third free throw is the same as not making the third free throw. So we have to write it that way, right? Not C. Then we use the formula. The formula says when we have a not, we replace it with 1 minus the event probability. So the first 2 free throws are still 2/3. We still multiply it, but it's 1 minus the probability of C. Type that into your calculator, you get 0.148. So it's actually less likely that he's going to make 2 and miss 1, right? Well, miss the third one. It's actually more likely he'd miss any one of them, but we're not getting into all that. All right, and last one. What's the probability that he misses at least 1 free throw? I'm going to let you guys try that one. That one might show up as a bonus problem on an exam or something like that. So I want you to give it a shot. You can ask questions in the discussion forum, but I'm not going over this one. You don't need it for the homework. So try this one on your own. All right, almost done. I know it's a long video, guys. Use the Rock and Roll Hall of Fame data in example 2 to determine whether being a female inductee and being a music performer are independent events. And part B, we're going to determine if these are disjoint events. So independent means if you know somebody's female, does that change the probability that they're a music performer? Or if you know somebody's a music performer, does that change the probability that they're female when compared to the entire Rock and Roll Hall of Fame? So what we're going to do is we're going to use the formula, the independent events formula from a few slides ago. So if a female and music performer are independent, then this formula will give us a true statement when we plug the numbers in. We've already computed all these values. So example 2 told us the probability of female and music performer is 0.125. Then we multiply probability of female, probability of music performer. Again, these were all computed in example 2, all 3 of these. We multiply this out and we get 0.105. And then we say, is 0.125 the same as these 2 multiplied together? Well, it's not. 0.125 is not really that close to 0.105. So these are not independent. So that means that if you know someone is a female and in the Rock and Roll Hall of Fame, it changes the probability that if you select that person at random, that they're a music performer, and vice versa. If you know someone's a music performer, it changes the probability that if someone is selected at random, that they are female. So this is sort of a independence test, and this data failed the independence test, which means it is not independent. So these numbers would have to be very, very close together to be considered independent. What about disjoint? Are female and music performer disjoint? Well, in order for them to be disjoint, then the probability of female and a music performer would have to be 0. Well, we know it's not 0. We computed in example 2 that it's definitely not 0. So because 0.125 is not 0, then these are not disjoint. And so this is fairly typical for the type of problem you're going to have to deal with. Just don't be in a big hurry when you're doing this homework, because I'm only going over one example of each of these things. Your homework goes into a lot more detail. So don't get frustrated. Just reread it and go back through it and think about what it means. And that leads me to the terminology caution. It's easy to confuse the concepts of disjoint events and independent events, but they are actually very different concepts. If A and B are disjoint, when A occurs, we know that B can't possibly also occur on the same trial. However, if A and B are independent, when A occurs, it doesn't change at all the probability that B occurs on the same trial. So disjoint means that A affects B in some way, right? If A happens, B can't happen. If B happens, A can't happen. But independent means something totally different. Independent means if A happens, then B just keeps doing what it's doing. Or if B happens, then A just keeps doing what it's doing. So independent events need common outcomes because they don't affect each other. They just do whatever they're normally doing. But disjoint events are not allowed to have common outcomes by definition. So you have some problems on the homework that deal with this. Use this, I don't know if it's a mnemonic or maybe like a hint. Use this way of thinking about independent events and disjoint events. It'll help you on the homework and on a test. So here's a summary of the probability rules. I just put everything in one slide. So if you're doing the homework, you can just reference this slide. And this is just stuff that will be like on the checklist for the exams. Just make sure you know all this. And of course, if you need extra practice, there are some in the book. P.1, remember, is way at the end of the book. But there's a lot of good exercises. A lot of these exercises, of course, are exactly the same as your homework problems. So that's it for this video. Long video, thanks for hanging in there. And next up will be the beginning of chapter 3. So until then, study hard, and I'll see you real soon. Bye-bye.